All right, hello everybody, and welcome to my basement. I'm giving you today a little demonstration here for our second experiment of thermodynamics, ME3331. And in this experiment today, we're going to be talking about steady state control volume analysis. I had originally intended for this laboratory to be done in the classroom and give everybody their own device to measure and their own ways of measuring this, like we did with the syringe experiments. But unfortunately, we don't have that. We don't have that this year, and so we're making do with something that we can do ourselves, and that I can do for you. Then I can explain how to do the experiment and give you the data. Okay. So yeah, so I'm down here in my basement, and I'm taking a look at this hair dryer. It's my wife's hair dryer. She's given me gracious permission to use it today in this experiment. I promised not to hurt it under certain penalties. And so yeah, so today I'm going to be kind of taking a look at this device and doing a control volume analysis of it. So let's go over a little bit of what we're going to be doing in the experiment. Okay. So the laboratory experiment I have outlined here on the sheet, which I will post on Canvas. All right, so the idea is that you're going to be watching this pre-recorded video of me doing this experiment, which you would have normally been doing yourself, but I think you'll get the idea. And you'll hand in the assignment individually for homework credit through Canvas by Monday, the 8th of March, Monday, 8 a.m. on March 30th, sorry. So yeah, so the idea here is that we have a hair dryer, which is shown here. It's a 1500 watt hair dryer. It has lots of bells and whistles. It has the ability to change the hair. I'll move over here. You can see it has the ability to change the power and different switches here, and it has the ability to do 2 different fan levels and has the ability to turn off the heater as well. So that's the first thing that we have available to be looking at. So if we look at the hairdryer itself, it's pretty much a device that contains a fan. It brings in air from this side. It goes through a fan. And then there's a bunch of heating elements that are inside the hairdryer, right, which then heats the gas. The gas being air. Okay, we're assuming it's an ideal gas. So what we're going to do is we're going to do an analysis to actually derive the exit temperature of the hairdryer. Okay, we're going to derive the exit temperature of the hairdryer by measuring a few things. All right, so what we're going to do is we're going to be measuring, first of all, we're going to be measuring the power that goes into the hairdryer. Okay, so the power into the hairdryer, I'm using this plug here, so I'm going to pull this off the wall. So that I have the hairdryer plugged into an electric current meter, which is an inline current meter that you can buy pretty easily from hardware store. Essentially, that goes into the wall, and it tells you how many watts of power that you're using for the hairdryer. This would be the work input to the hairdryer, right? So both for the heating element and the fan. Okay, plug that back in. And then the other thing we're going to be measuring from the hairdryer is the velocity of the air coming out of the hairdryer and the velocity of the air coming into the hairdryer. Okay? And to do that, I'm going to be using what's called an anemometer. So this is an anemometer that they use in HVAC, or heating, ventilation, and air conditioning. Anemometers are a pretty common instrument. Essentially, you can see what's happening here. This fan is blowing. So if you blow in there, you see that the velocity increases, and I can turn it on, and we can take a look. Yep, turn it on, and you can see here. And if I turn the light on for you, okay, so you can see the light, and I blow in. Oh, you're seeing it backwards. You see the velocity increases in meters per second. Now notice that this anemometer also tells us the temperature of the air in the environment, as well as the relative humidity. We are not going to be using the temperature because the temperature is measuring the room temperature in here. So the room temperature, and at the bottom, I think the temperature takeoff is somewhere in the back here somewhere. So it's actually not going to be taking the temperature of the gas coming through here. I learned that when I did the first dry run of this experiment. Okay, so it's giving us the velocity in meters per second, and it's giving us the temperature of the room. So we're going to read the temperature of the room, and we're going to put it in our notes here in our data, and we're going to read the velocity inlet and outlet of the hairdryer. Okay, so and we're going to be taking these data. All right, so now the idea is to solve for the exit temperature, knowing the power, the velocity, and some air properties that we know already. So you might wonder, okay, what do we know? So the things that we're going to need to know for this problem are here on the assignment sheet. And so what we need to know are the diameter of the inlet duct. And you might wonder why we need to know that, but if you remember how to solve for mass flow, you know that we need to know the area of the inlet duct. So we need to know the diameter, which we'll measure here in a second, the ambient temperature, which, as I said, is being measured by my little device here. It's downright cold here in my basement, so it's about 15.3 degrees C. So I'm going to go ahead and write that on my sheet here in a minute when I get to it. And then we also need to know ambient pressure. Okay. And then what we're going to do to conduct our experiment, just to go over this, is that we're going to record the ambient temperature, pressure, and inlet duct diameter. We're going to turn on the hairdryer here that I have mounted to a nice stand. You can see I have it mounted to a board with my data collection, down here, and a few other tools that I have laying around. All right, so we're going to do that, and we're going to record the ambient temperature, pressure, and inlet duct diameter, and then we're going to turn the hairdryer on to a desired setting. In this case, we have this hairdryer, as I said, is pretty fancy. We got 2 fan levels, and we got 4 heat levels. We have no heat, which is a button that I can press here. We have low heat, medium heat, and high heat. Now, I don't know why. I don't usually blow by dry my hair. I don't know why one needs to have 3 different heat settings, but maybe you do. I don't know. What we're going to find in our calculations is how to find the exit temperature of this thing. Of course, I could always measure the exit temperature, but that wouldn't be very fun, would it? Okay. So now, let's see. We're going to record the exit velocity and temperature, and we're going to repeat 2 through 4 for the remaining power settings. I could finish this. Okay, remaining power settings. Okay, good. All right, so now this is our experimental data sheet like we did last time. And then at the end of the experiment, I'm going to do the experiment, and then I'll talk to you a little bit about the analysis that you'll be doing for your homework assignment. Okay, so let's get to it. Now, first thing is first. Okay, I have my tablet here that has it has all these things on it that we need to know. So I'm going to write these down in my tablet. Like I usually do for lecture. Let's see, I can make it a little smaller, but I don't want to make it too small so you can see what data I'm putting in here. Okay, and I also want you to see me and the experiment, so we want to make sure we get it all in here. Okay, so that's first things first. Let's measure the diameter of the duct. To measure the diameter of the duct, I'm going to use this dial caliper that I have of my own. As we know, in dial calipers, you always first make sure that the indicator is pointing at the 0 mark, and then what we'll do is we'll measure it out here. I got to move my hairdryer a little bit so I can measure it. So what I'm going to do is I'm going to measure the duct. So I'm going to be measuring the velocity, not like inside there. Notice there's like a screen that's preventing lint and other things from going in. I'm going to be measuring the duct diameter here, probably at the outside. So I'm going to measure it like right at the outside of this, the flat part of this thing, and I'm measuring that to be about 2 point. So if you look here, now if you can see it very well, I don't know if you can see it very well. So you get the 2 right there, and then there's 2.19, which is the reading that we have here. So I'm going to go 2.19 for the diameter of the duct. So let's see. So 2.19 inches for the diameter of the duct. Okay. Now the next thing to do is find the ambient temperature. The ambient temperature here we can read on my handy little anemometer, and it says that it's a chilly 15.6 degrees Celsius here. So that's what we have. Okay. Now the next thing is ambient pressure. Now a good thing about ambient pressure is that ambient pressure generally doesn't change very much. Too much junk on my bench down here. Okay, doesn't change very much location to location. For Minneapolis, we're just going to use whatever the Minneapolis value is, and I looked it up here. It's 28.97, as you can see here on the weather site here. And yeah, so okay, so we're good to go. So let's see. Then we're going to essentially here take that, and then we're going to go. I have it in kPa, but I've already done the conversion for you. I wrote it down on my board here. It's 101.15. So 101.15. So that's our pressure. Now I'm just going to go through doing the experiment. And and you can watch as I take the data, and we'll go from there, right? So I may not fill out this entire chart while you're watching. I may do this after the video is recorded to save a little bit of time for you guys, because it gets a little repetitive, but at least I'll do the first round, and then I'll explain how to do the analysis. And then I'm sure you guys will have plenty of questions. You can ask me an email or whatever. Okay, so let's do it. All right, so what we're going to do is first I'm going to turn on the hair dryer here, and we're going to start at the lowest fan speed, as it says here. So we're going to start with low fan speed and no heat. So which is me pressing the button essentially. So you just follow my procedure here. Okay, so I got the fan on the low speed. Feels good. My hands are cold. Okay, it's on the lowest heat setting right now, but we're gonna switch it off essentially and read the power. So if I just press the button, you can hear the fan go a little bit higher in speed. I read 154 watts. Okay, so I'm going to record 154. Now I'm going to record the inlet velocity, and that's recorded here. Notice there's an arrow on the back side of my anemometer. I'm going to put it here at the inlet side and see what kind of velocity it's measuring. Measure it right. Essentially here I have a velocity of 4 meters per second, about 4.0. Okay? The next thing we're going to do is measure the outlet velocity with the heater off. About 9.6. Okay, so then that's what we have. Now I've got the heater on its low power. Make sure it's on its the lowest power setting. Okay, the lowest heater setting. And now I'm going to look again at the power. So this is reading 430. Okay, and then we're going to measure the airflow again. Now I shouldn't expect it's going to be very different, but we're just going to take the data anyhow. Okay. I'm getting about 4.4. It really depends on where I have this thing tilted, right? We're making a pretty rough measurement, so it'll all work out in the end, okay? So velocity maybe not that big of a difference, but we're going to see. So 9.5. Okay, now we're going to go to the next heat setting. All right, now it's pulling down a little bit more heat. You can feel the air is a little hotter coming out of it. We have 526 watts. Okay, got 526 watts, and I measure the velocities again. So inlet velocity. Oops. Seems to be creeping up a little bit, but I think that just may be the way I'm holding this thing. Okay, it's now about 9.7. Okay, so you notice that the velocities are pretty much staying the same, which is kind of interesting, right? And then we go to the highest. We go to the highest setting, and that's nice and toasty. Okay, this fan is still at the low setting. We have 850 watts. Okay, and then I'm going to pull out my velocities here one more time. I'm getting about 4.6, and here Oh, we got about 9.9. Okay, so it's approximately the same for those different settings. Now let's go ahead and move on to the highest settings. We might as well just get all these done while we're here, so just to have all the data we need. So I'm going to go to the higher setting. I'm going to cool it down. I'm going to cool it down by pressing the button. It's going to be a little tricky here since I have limited hands. So the power meter is saying about 293. So it's about 293 for that. Now let me figure out what the velocity is. It's about 7.2. And if I look at what the exit velocity is, about 142. I mean 14.2. About 14.2. Okay, so now we get the lowest heat setting. Let's do it again. 841. .1 and outlet. .8. Okay, then we have a couple more settings to do. And one more setting. All right, great. So we just took all the data that we need here. See, people are handing in discussions because you know exactly when I'm doing this presentation. So you can see here now that we have all the data. I will provide these data to you. I'll probably type them into your sheet, okay, so to make it a little bit better. You don't have to read my handwriting. Yeah, from there, essentially, we have just a few more things we can do here. So let's see here. We can look at what we need to do for the assignment. Okay, I probably talk quieter now because the fan's not going. Okay, so required analysis. Let's see. What are we going to do with these data that I just took? Okay, so I just took those data for you. Ordinarily, you'd be doing it, but I think you see that it's not that difficult. Okay. So on separate sheets of paper or in a computer document, you can do it however you want. You can do it like the way you did it last time. You can copy this sheet, which is fine. I'll leave the Word doc. You can just use this sheet if you want. I like to use an Excel spreadsheet. I actually used Excel to do the analysis of my first data set from here, and it worked out pretty well. Just make some, at the end, I think for number 6, you're going to make a plot. So just want to make sure you know that. Okay, so here's what you're going to do. Number 1 is that you're going to make a diagram of the experiment, indicate your thermodynamic system. You're going to state the assumptions that you'll make when performing the analysis. This is super important. We do this for all homework assignments. Remember that this is a steady state device. It's a control volume. You need to draw your control volume, okay? I want to see some awesome hairdryer pictures out there, okay? I want you to do a really good job making your hairdryer diagrams. Okay. From the inlet velocity and ambient conditions, use the ideal gas law to calculate the mass flow rate for each setting. That's why we needed the area for the inlet, remember. Record all of your calculated data in table 2. So I gave you a table to put all your calculated values. Okay, so I could tell you what the outlet diameter of the hairdryer is, but I'd like you to use your average data, okay, to determine what the diameter of the outlet duct is, okay, using all the things that you know. Okay, the next thing is, when you're doing this, make sure you think about the average, right? You don't need to use the one value. There's no different areas. The area is the same. So the idea would be, okay, so for a given mass flow, what's the area? And then you might actually have some error, experimental error that you discuss, okay? So I want to hear you discuss, I want to see you in your writing discussing some of the experimental errors that you might encounter. Okay, then you want to use the first law of thermodynamics for a control volume to calculate the exit temperature. Okay, so this is the main part. So you're going to use the first law for a control volume in order to derive the exit temperature. All right, so if you're getting temperatures in the 200 degrees C range, there's a problem, okay? Your temperatures are not going to be that high. Okay, so just be careful. I think you make sure you're using the right correction factor, especially on the velocity term. There's a 1000 in there, remember, that we did in our homework assignments. All right, and the last thing to calculate would be assuming that the fan power remains constant for each fan setting, determining the power required by the heater section. Remember, there are two separate pieces in here, right? There's the fan, and then there's the heater, right? So in that case, you want to be able, you can actually use the no heat value to determine what the heater power is. Okay, so the fan's going to have some wattage requirement, and then the heater's going to require some power. Okay, so that's just a matter of subtraction. And then number 6 is to perform an analysis of your results. Plot using Excel or other graphing software the outlet temperature versus heater power for each fan. So there's going to be a couple sets of data. So I want to see 2 different lines, one for each fan, low fan, high fan. Okay, don't put them all together. But you put them on the same plot, but just have them 2 data sets, okay? Make note of any experimental error that you observe. So what kind of error are you observing? For instance, on the error for the area, calculation, did you observe some error there? And maybe what is that error? Quantify it using standard deviation or something like that. Are the trends linear? Do you see this temperature versus heater power as a linear function? And if it's not linear, why not? And if it is linear, why do you expect that? So I want to just hear a little bit of why you see that and what your observations are with regard to that. So do you have any, if you have any observations regarding the adiabatic assumption, because notice at the top, I don't know if I mentioned this in the words, but notice at the top it says, we assume that we use an ideal gas, air is an ideal gas with constant specific heats, and that the hairdryer has negligible heat loss to the environment compared to the power input. So what I'm saying is that this thing is not losing that much heat. I mean, it's warm to the touch, but it's not hot, right? Most of it is in enthalpy. Most of it is in the air coming in and then the hot air coming out. That's where most of the power is, as well as the heater element and the power coming in. So maybe you want to test that assumption. Is that a valid assumption? Is that not a valid assumption? Maybe you want to discuss that a little bit. You'll be graded a little bit on how you discuss this and what kind of observations you make. And any other observations that you might have, you should put in there. I'm not expecting more than like a paragraph of discussion, so I don't want you to write like a whole report on this, but I just want some sort of discussion. So this will suffice for your homework for Monday morning. I'll also be posting a lecture on new material from chapter 5, but there will be no homework attached to that. So that'll be a quick lecture that I'll also post for Monday morning to go along with the survey and everything else we do. Okay? Well, I hope you enjoyed my basement experiment, and good luck doing this experimental analysis, and I'll hope to hear from you soon if you have any questions.